for a given x of n, the Z transform x of z is defined like this. And the maths people call this as, anyone knows what this is called by them? Ztransform. No, not quite. Generating functions. And Ztransform is the other commonly used term. So this is almost as if God given. Here is the Ztransform, take it. Whereas we can motivate this in a slightly different manner from what we have learned so far. So the way we would like to think of this is like this. Here we have a system its impulse response is h of n. To this we feed this everlasting exponential z0 to the n, and y of n of course is nothing but z0 power n convolved with h of n. So this is nothing but x of n minus k, which is z0 n minus k, h of k, k going from minus infinity to plus infinity. And because the summation involves only k, we can take z0 to the n outside. So this is h of k z0 to the minus k summed up over all k. Now this when you sum up over all k, this is not going to depend on k. It surely will depend on h, little h. To show its dependence on little h, we will denote it as cap h. It will also be a function of z0. So we call this as h of z0. And hence y of n is nothing but z0 to the n times h of z0. Of course, we are assuming that this infinite summation exists, and we call this as h of z0. So if you look at this particular output for the given input, the input was z0 to the n, output also is z0 to the n, except that it is modified by a constant which is complex in general. And if you apply an input to an LTI system and you get exactly the same signal as the output except for a scale factor, signal is called, so this is called as an eigen signal. So this parallels very closely another way of looking at Laplace transform in continuous time. There the eigen signal takes the form e to the st, and if you apply it to a continuous time system with impulse response h of t, you will get e to the st back except it is multiplied by a constant, namely h of s, and that h of s is called as the bilateral Laplace transform. So, this is exactly along those lines. So, just to show the parallel here, if you have e to the st s naught t, and if you apply this, and you will see that y of t is e to the s naught t times h of s naught, and h of s naught is nothing but minus infinity to plus infinity e to the minus s naught tau h of tau d tau. And this is the bilateral Laplace transform. And this should also immediately tell you something. Do you see a problem here between Laplace and Z, the way we have been using the notation? Of course, the mathematicians will be appalled by this, but we take it in our stride. We are so much used to it, any other notation will seem not quite what it should be. So, what I want you to realize is we are using the independent variable to tell us what the transform is. When we say h of z, we say z transform. When we say h of s, we say it is the Laplace transform. S is after all the independent variable, and s is a complex number. Here z also is a complex number, right? And so both Laplace transform and Z transform are complex functions of complex variables, right? And merely calling the independent variable as s does not make h of s the Laplace transform, whereas calling it as h of z does not make it as the Z transform. So, if you want to use more precise notation, there are some books that use this. They denote x of z as xz of z. Some books that are more careful use this, and they will call this as HL of s. So, one more change in the notation is used, not merely relying on the independent variable to tell us what the transform is. But as far as this course is concerned, we will continue to use x of z or h of z to denote the Z transform, and when we write h of s, we will mean the Laplace transform, bilateral Laplace transform. But you need to be aware that this is not quite good notation, it is sloppy, but that is well entrenched in the literature. And moment you have an infinite summation, you need to worry about the existence of this, all right. So, the values of z for which the Z transform x of z exists is called as the what you are already familiar with. In the Laplace transform case, it is called as the region of convergence and abbreviated as ROC. In the bilateral Laplace also, you had to worry about region of convergence. Moment you have that definition, a simple minded application of the formula is x of n being a to the n u of n. X of z of course is n going from minus infinity to plus infinity, x of n z to the minus n. In this case, x of n happens to be a to the n u of n, and because u of n is there, we can get rid of u of n and then limit our sum from 0 to infinity. And if you simplify this, this is nothing but n going from 0 to infinity a z inverse power n, and this is a simple geometric series a times r to the n, and the answer is a by 1 minus r geometric series. So, this is nothing but 1 by 1 minus a z inverse. This of course assumes that the geometric ratio is strictly less than 1. You need mod a z inverse to be less than 1. So, this is the same as mod a strictly less than mod z, or it is usually written like this, mod z strictly greater than mod a. So, here is an example of a simple geometric sequence a to the n u of n having this Z transform, and the only reason why this is the first example is because we really want the second example to be this, alright. So, now we have x of n to be minus a to the n u of minus n minus 1. So, what is its Z transform? So, this is because you have u of minus n minus 1, the summation goes from minus infinity to minus 1, a to the n z to the minus n, and if you simplify it, what will be the answer? So, you can now make a change of variable L to be minus n. The only difference of course is the condition under which this is valid turns out to be now mod z less than mod a. Therefore, this tells you that the algebraic expression of the Z transform alone is not enough to pin down the time domain sequence for which this is the Z transform of. You also need the associated region of convergence. So, if I tell you the Z transform is 1 by 1 minus a z inverse, tell me what the corresponding sequence is, you will not be able to tell me the answer, because unless I tell you whether it is mod z greater than mod a or mod z less than mod a, you will not know whether the sequence is a to the n u of n or minus a to the n u of minus n minus 1. So, this is absolutely no different from what was happening in the continuous time case with respect to Laplace transform. There you had e to the at u of t, its Laplace transform was 1 by s minus a, and the region of convergence was real s greater than real A, and what was the corresponding counterpart? It is e power at u of minus t. Anything else missing here? You have minus sign, and then this is real S strictly less than real A. So, now you see the parallel between Laplace and Z. There you had two functions which had identical algebraic expression for the Laplace, they differed only in the region of convergence. So, this counterpart in the discrete time case is a to the n u of n and minus a to the n u of minus n minus 1. So, the Z transform is a power series, and in at least textbook examples you will find that this power series has a closed form expression and associated region of convergence. So, typically power series will have algebraic expression plus ROC. Suppose you had x of n to be minus 1, 2, 4 pi, and we will use this arrow to denote that this is the n equal to 0 term. The corresponding x of z, all you need to do is merely apply the definition. So, this is minus 1 plus 2z inverse plus 4z to the minus 2 plus pi times z to the minus 3. And for what values of z is this expression valid? So, in the previous example when we saw a to the n u of n, we found that that was valid only for mod z greater than mod a. So, here is a simpler example, and this is valid for what values of z? So, z equal to 0 does not belong to the region of convergence, and immediately you can see variants of this. Suppose you had this as the sequence, except now this is the n equal to 0 term, x of z will now be minus z plus 2 plus 4z inverse plus pi times z to the minus 2. And for what values of z is this valid, or what values of z this is not valid? Again z equal to 0, this will blow up, and then for which other value of z will this not be finite? So, both 0 and infinity are not part of the region of convergence. So, all other values are, and the final variant is this. So, this is the n equal to 0 term. So, clearly x of z is minus z cubed plus 2z square plus 4z plus pi, and the ROC will exclude infinity, right. Therefore, z equal to infinity will not belong to the region of convergence. So, later we will see that this is a general property of finite duration sequences. When you have a finite duration sequence, then the region of convergence will be the entire z plane except possibly for 0 and or infinity. So, later what we will do is we will start to look at ideas like poles and zeros, and these are no different from the concept of poles and zeros that you had encountered in the Laplace transform case.